Welcome back, everyone. So we're just gonna jump right on into it. This is the next video in my Requiem for Transmission series. You may remember in the last one I built the shift controller to control the shift solenoids in the transmission. In this one, I'm going to be making a driver to control the line pressure solenoid in the transmission. Now, as I mentioned in the last video, I need a pulse width modulated signal to control this solenoid because it's not just an on or off, open or close kind of thing. You can vary how far open or closed the pintle is in there based on the overall power delivered to the solenoid. And through that, of course, you can control the line pressure in the transmission. So pulse width modulation is pretty straightforward. There's a set frequency, which is the number of pulses you have per second since it's measured in hertz. And then what you're trying to do is change the width of the pulses. You can see if all of these pulses are very short, then the overall amount of power delivered to our solenoid will be small. And if we open them up all the way, well, then the overall power delivered to the solenoid will be much greater. So we're trying to get a set frequency and a variable pulse width. So how am I going to generate this pulse width modulated signal? Well, if the comments on my last video are anything to go by, I'm sure a bunch of you were saying, why don't you use these servo motor drivers? Why don't you use these pre-built modules? Or how about, why don't you use an Arduino? And I mean, you're totally right, I could. I could even use the GPIO pins on my flipper if I really wanted to, but I have a much more classical sort of approach to this problem. That's right. It's a 555 timer. So in case you're unaware, the 555 timer is one of the most ubiquitous ICs out there, and there's near endless documentation on how to use it in all kinds of situations, not just pulse width modulation. So I'm not going to go into too much detail on how this circuit works. For our purposes right now, all we really care about is how much control I have over the pulse width and how much the frequency drifts. It actually is working surprisingly well. Between 15 and 98% duty cycle, the frequency stays around 8 to 10 hertz. But as soon as you go below 15% duty cycle, you see the frequency just falls flat on its face. But I think I'm going to stick with this design. Let's see if we can implement it. Alright, so I just threw in a MOSFET here. It's a IRF 510N. Just kind of whatever I had on hand, honestly. And so I'm scoping the output of the MOSFET here. And you can see our rectangle wave is looking really nice. So I got a diode here for protection. Let's go ahead and drop on our solenoid. Alright, well, it's clearly working. So we're dialed all the way down now, and I'm going to slowly crank it up. And you can see the pulses are really slow. I forgot to mention that the 8 to 10 hertz is unbelievably slow. I was expecting a couple hundred, so I might end up tuning this circuit to get the frequency up a bit. That would get rid of the jitters. So while I was playing around with this circuit trying to get the frequency up, I noticed that the higher I made the frequency, the more noise and distortion I was getting on my output. So I just abandoned that circuit. I went back to an absolute classic. I'll throw up a Dave's Cat example for any of you guys playing along at home. So I've only made a few changes. I'm using monolithic ceramic capacitors. The one on our control voltage pin is 0.1 microfarad. Our main timing capacitor is 47 nanofarad, so that's 0.047 microfarad. And the trimmer, I bumped up from 10K to 20K. On the output, I was using this Chinese knockoff international rectifier. It's a 510N. I was a little concerned that might have been causing some distortion, so I switched back to one of my NTEs. This is a 2985. It's meant for high-speed switching. And now with those changes, you can see we're about 1.2 thousand hertz. And you can see our waveform is looking pretty good up there. So we're going to go ahead and test this thing out. Alright, so I got my automotive leak tester set up. This is going to show us the amount of flow. So as I start rotating the potentiometer, you can see we're reducing the amount of overall flow. I'm going to turn it the other way, and we're increasing the flow. And I can control it pretty precisely. If I want to put it to 80, there's 80. If I want to put it to 60, there's 60. We can go up all the way. We can go down all the way. So now, since things are looking good, we've got our frequency is a little over 1K, and we have good control over the position of the pintle. Now all that's left is I got to convert this circuit that I'm currently using to a design I can apply to a prototyping board, and then we just gotta mount this thing up. And here it is assembled. So I did do this on a live stream instead of putting a montage in this video. I figured I'd do it on a live stream. So if anybody wants to watch that, I actually assembled this one on the live stream, and then when I went to test this, I cooked it. But luckily, through the magic of making two of them, we have this one. So now I'll throw up a diagram for any of you playing along at home. Now we got 12 volts applied to these terminals right here, which of course run our 555 timer. The output from the timer goes through this resistor to the MOSFET, and the source and the drain on the MOSFET are just these terminals right here. I added in this rectifier diode just to help suppress any back EMF from cooking the MOSFET. And of course, you change the pulse width by adjusting the potentiometer. So after hearing all that, you might be saying, well, wait a second, you're protecting the MOSFET. Well, what are you doing to protect the timer? Well, that's where this voltage regulator comes into play. This is both a buck and a boost converter, so it'll maintain 12 volt output whether the voltage goes above or below the target. So now here's how everything's going to be hooked up. Now don't forget, we're still in the prototyping phase, so I'm powering this whole thing off the cigarette lighter, and you might notice there's 3 wires coming out of here. Well, that's because there's a positive and a negative running the regulator, which runs the timer. The 3rd wire is for the ground, which is coming into the MOSFET. And so all of that means, all I have to do is extend the 1 wire that comes back from the EPC solenoid and run it to this terminal right here. And then I just plug this into the cigarette lighter and boom, I've got control over line pressure. So real quick, I just want to do one final test with our stand-in line pressure solenoid, and then we'll hook this thing up to the truck. So let's go ahead and test it anyways. I'm gonna start closing up the solenoid here. That's fully closed, so oh, there we go, 80, I'm sorry, 60, back to 60, now let's do 80. Open it all the way, close it up all the way. Alright, right in the middle, let's do 70. Now, the control does feel a little more finicky, but I definitely still have good control. So let's go ahead and test this thing in the truck for real. So the hookup couldn't be simpler. You see that gray connector right there is my old setup to control the shift solenoids. And then this red wire is where I tapped in for the line pressure solenoid. Now this is the return. There's another wire going through this harness that comes from the PCM, and that supplies positive to that solenoid at all times. So I just need to hook this wire up to the ground on my MOSFET. Alright, so the line pressure solenoid is hooked up to the ground on this. So all we gotta do is fire the truck up. Alright, so we're starting at the bottom of the scale. Let's go ahead and crank it up. It doesn't feel like we have very good control. Yeah, see, there's a huge dead spot right here. Oop. That seems to be the line. Yeah, so it's basically wide open or closed all the way. And I don't have much control of anything in between that. Okay, so let's watch our waveform while I play with the knobs. See, we still have full control here. Interesting. I mean, I have, my control is limited to either the lowest or the highest, and I have no control in the middle ground is what I'm getting at. Well, that was disappointing. I mean, I do have control over the line pressure solenoid. As you can see, I set the pulse width to its minimum. We got our lowest reading. I set the pulse width to its maximum. We got the highest reading. Got power, got ground. Waveform looks good. So I believe there's some other thing in the transmission that's causing these erratic readings and causing me to not have fine control of the pressure between the minimum and maximum. Because, I mean, there's all kinds of spools, check valves, accumulators, all kinds of funny stuff in there that could be causing issues. But I'm going to have to leave it to another video to show you how I diagnose and fix this problem. And there's plenty more things to do on this project as well, because I want feedback over transmission fluid temperature and a few other things. I want to upgrade the shifter, and we got to fix this problem we got now. So if any of this stuff sounds interesting, you know, maybe flick it, twist it, pop it. We'll see you next time.
All right, let me ask you, Rob.
All right. I missed it.
What?
I couldn't find you.
You suck!
Ah, man. Alright, hopefully that's enough.